Cover up the 4. What's sine of 0? So what I'm asking is, if you look at the unit circle and you go to an angle of 0, then what is the y-coordinate? 0. And then multiply it times 4. 0. Right? 0, right? Okay. And then you go to pi over 2. So sine of pi over 2, that's the y-coordinate at pi over 2, which is 1 times 4. 4. Hey, that's a 4. Pi, right? What's sine of pi? So now you're over there, right? What's the y-coordinate over there? 0 times 4. 0. And then finally 2 pi, you're back to the beginning, right? Oh wait, I missed one. 3 pi over 2. 3 pi over 2 is straight down, right? What's sine of 3 pi over 2? What's the y-coordinate there? -1. Do y'all see why knowing the unit circle just makes this, like if you still can't see the unit circle, which, you know, you'll build up to it, but if you're not there yet, this is a little slower process, but once you like can visualize the unit circle and stuff, everything's gonna flow a lot better. So what's my answer? It was -1 and then times 4. So -4. And then finally 2 pi. We go all the way around. Sine of 2 pi is 0. So what I'm going to do is plot these points now. At 0, I'm at 0. At pi over 2, I'm up at 4. Wait a minute. I thought I told you you had to be between -1 and 1. I did. That has to be between -1 and 1. If you come and multiply by 4, then of course it's not going to be between -1 and 1 anymore because you've scaled it, right? You've stretched it out. And so that's what our graph's going to look like. Here's 4 up here. At pi, we're at 0. At 3 pi over 2, we're down here at -4. And then at 2 pi, we're at 0. And it's still going to look like the same sort of curve. It's going to go like this. When you draw a sine curve, it's not this, okay? It's not a jagged V shape, W shape, whatever you want to call this, okay? These are curves, right? There's arcs to these. If you compare that, that's what the graph of that is. If you were to go to 1 here and -1, the normal sine function, right? The regular old sine function would look like this. That's what the normal sine function would look like. So putting a 4 there, what did it do? Why did I do that? That's supposed to come to here. There we go. So what multiplying it by 4 does is it leaves these points, it leaves the x-intercepts in place. Do you all see that? The x-intercepts have not moved. The x-intercepts of that graph have not moved. And then what it's done is it's taken this arc of this sine and it's pulled it up and it's pulled this one down. And so that distance from the x-axis to here, that distance right there, we call this the amplitude. And the amplitude of the sine function, sorry, that's, so if you have f of x equals some number a in front of the sine function, all right? So for us, that problem there, I let the a be 4, right? The a in front is called the amplitude. Actually, it's not the a, it's the absolute value of a. The absolute value of a is equal to what we call the amplitude of the sine curve. So do y'all feel like you understand what the number in front of that is doing? Stretching it? What if I put a number in front that's something small, like 1/4? Instead of 4, 1/4. What do you think that's going to do? Shrink it down, right? Shrink it down. Was there a question? Yes, what's your question?
The amplitude is from 0 to 4.
Yes.
Not from the red line to the purple.
Yeah, and another way to kind of think about this. Yeah, the amplitude has nothing to do with this curve. The amplitude is really this distance. If you were to measure from here, the top peak, to the bottom, right there, that distance from there to there, the amplitude is half of that. So this from here to here is 8, right? Distance-wise, the amplitude is 4. I don't want to say it's the distance from here to here because in a little while, not today, but later on, we're going to move this graph up, down, left, right, squash it, flip it. We're going to be doing things, and the x-axis won't always be our reference point for the amplitude. The amplitude can always be looked at as being half of this distance, though. For us, though, algebraically, it's always the number in front, the absolute value of it. Okay? Questions here? So I said, if this is a 1/4, y'all feel like that's going to squash it down? It will, right? What if I put a negative in front? A -4. Flip it. Oh, I shouldn't have done that. I'll do it anyway. Okay. So what if I did f of x equals -4 sine x? That's going to have the effect, our table will look exactly the same as the last table, right? Well, not exactly the same, but a lot of it will, right? When we plug in 0, we'll still get 0, won't we? But when we go to pi over 2, sine of pi over 2 is 1, but then we're going to multiply it times -4. So now this is going to be -4. Then this will be 0. Then at 3 pi over 2, that's where your angle is straight down, right? Your y-coordinate down here on the unit circle is -1. And so when you put sine of 3 pi over 2, you get -1 times -4. That gives you +4. And then 0 again when you plug in 2 pi. So that has the effect of putting all these x-intercepts are in the same place, right? But it's these two values that now change positions. So instead of being up here, it's down here. Instead of being down here, it's up here. And now your graph looks like this instead. So it had the effect of flipping it over reflecting it over the x-axis. So a negative out front, okay? So if a is less than 0, right? If a is less than 0, if that number there is a negative number, then it's a reflection, right, over the x-axis. If a is positive, then it's going to look like your regular old sine function. Yes?
So is the amplitude always going to be positive?
Your amplitude is always positive. Good question. See here, I put a -4, right? But by definition, the amplitude is the absolute value of that number. So the amplitude of that green one I drew is also 4. All right. Are we doing all right? Yeah? So far? All right, I'm going to change it up a little bit. I want to know now we've done 4 sine x, right? We did -4 sine x, and I talked about what would happen if you put 1/4 out there, it should get shrunk down, right? We haven't talked about this though. What if I put the 4 inside with the x? Let's see what happens here. Things are about to get interesting. Well, interesting, I don't know if interesting is the right word. Y'all see that the 4 is inside there with the x now? Let's try a t-table, and let's go to our common points that we know. Here we have pi over 2, 3 pi over 2, and 2 pi. Let's try it out. What happens when you plug in 0? So what's 4 times 0? 0, right? And then what is sine of 0? What is sine of 0? 0, right? This is saying, that's a time. That's times right there, right? All I'm doing is plugging 0 in for x. 4 times 0 is 0, sine of 0. Okay, what sine is which coordinate? Y coordinate. Y coordinate at angle 0, which is 0. All right, so far, that's what the other sine functions have looked like, right? Yeah? Okay, what happens when we plug in pi over 2? Sine of 4 times pi over 2. What the hell? Okay. That's 4 pi over 2, right? 4 pi divided by 2. How many pi's is that? 4 pi divided by 2? What is that? 2 pi. What's sine of 2 pi? 0 again. 0. Right? Do y'all buy that or no? So at pi over 2, we're at 0, aren't we? What the heck? Okay. What about at pi? What happens when you plug pi in here?
0.
You get sine of 4 pi, right? That's what happens when I replace that x with pi. And sine of 4 pi, where's 4 pi on the unit circle? Where's 4 pi? That's 1 pi, 2 pi, 3 pi, 4 pi. So we're here, right? Sine there is?
0.
Shit, man. Right? 0, 0 again? What's going on here? This is weird. They're getting 0 every time. How about here? If we plug in 3 pi over 2 into that. Sine of 3 pi over 2 times 4. I should have put the 4 in front. It doesn't matter. What is that? Sine of 6 pi? Sine of 6 pi? Don't know what I'm doing here, right? Just 3 times 4 is 12. 12 pi divided by 2 is 6 pi. Where's 6 pi over there? All the way around back to 0 again, right? What the heck? And if you plug in 2 pi, it's going to be 8 pi, and that's 0. What the? Okay, maybe we made a mistake. Nothing is happening, right? It looks like nothing's happening. So I'm going to go to the graph over here, and I'm going to graph sine of 4x over here for you. Ready? The red one is the sine function. Okay, the red one is the regular old sine function. And sine of 4x is the blue one. What happened? What does it look like happened? How many complete cycles on the red one, between 0 and 2 pi, how many complete cycles do we have on the original red one? One cycle on the red one, right? It just goes up and down, that's it. One time between 0 and 2 pi. But the blue one, between 0 and 2 pi, how many full cycles? 1, 2, 3, 4. 4 of them, right? So it's completed 4 complete cycles, or what we call 4 complete periods, in the same amount of distance or angle that the original sine function took to complete 1 cycle. So it's almost like we've shrunk it down, or like compressed it. Here, this is kind of a cool thing I can do on this software. I can control the variable in front of the x. Can you all see this? It's in green. Watch what happens. Right now, the number in front of the x is 1. I'm going to make it bigger. There it's 4. The bigger I make it, the more cycles it completes. Make sense? What if I make it a smaller number, smaller than 1, like a fraction? What does it do? Ooh, it stretches it out. You see that? So somehow, the number in front of the x is controlling the cycle. How many cycles occur? And that cycle we call the period. What's the normal period for a sine function? The regular old sine function, how long does it take for it to complete 1 period? 2 pi, right? So for sine of x, the period of this is 2 pi. That means it completes 1 cycle, 1 complete cycle between 0 and 2 pi, right? That's for the regular sine function. This one, what's happened is it's completing it in 1/4 of that space. All right? In 1/4 of that space, it's completing the cycle. So how are we going to graph this? Let me see what my time, how's my time? 9 minutes? Yeah, I can keep going. All right, so I'm gonna say right now, this right here didn't really work, right? To do what we did before, to go 0 to 2 pi and just start plugging in the common angles that we're familiar with, it didn't give me a graph that I can really work with, all right? So how do we do this? What you're going to do is this first. You're going to take this in here, 4x, and what you're going to do is you're going to set that equal to the important points that we know are on the regular sine function. 2 pi, pi, pi over 2, 3 pi over 2. You're going to figure out, and 0, sorry, there's 5 points, right? You're going to try and figure out, first of all, when is this equal to 0? So I'm going to take this and set it equal to that. Then I'm going to say, when is 4x equal to pi over 2? And then I'm going to say, when is 4x equal to pi? Then I'm going to say, when is 4x equal to 3 pi over 2? And lastly, when is 4x equal to 2 pi? You understand what I've done here? I've taken the thing inside this sine function. This thing inside actually has a name. This is called the argument of the function. I'm taking the argument of that trig function sine, and I'm setting it equal to the 5 critical numbers that I use whenever I graph sine functions. And then I'm going to solve each of those for x. So what is solve for x here? What do? Divide by 4. So if you divide both sides by 4, you get x is 0. Okay, that's the first critical number that I'm going to use to graph. Solve this for x. What do you get? Divide both sides by 4. What do you get?
5 over 6.
Almost. Pi over 8. Pi over 8. Divide that, not divide that. Solve that for x. So divide by 4, and you get pi over 4, right? Last one, or second to last one, you get x is, what happens if you divide both sides by 4 here? 3 pi over 8. And lastly, we divide that one by 4, and what do you get? X is 2 pi over 4, so just pi over 2. So what we're doing here is this, just so you try and understand what's happening here. Here's a normal sine function, right? Our normal sine function looks like this. At 0 it starts, it goes up to 1, comes back to 0, down to -1, and then back to 0. That's what our normal sine function does between 0 and 2 pi. But because we've changed the number in here, it's doing that, but it's doing that at these numbers instead of those numbers. So instead of, this happening, well, this does happen at 0, right? But this peak right here that we have is not happening at pi over 2. It's actually happening at pi over 8. And then this one right here is not happening at pi, it's happening at pi over 4, and then so on and so forth. So now I'm going to draw it, all right? I'm going to try and draw this for you. The final picture of this. So I look at my answers and I say, okay, this is 0, and this is pi over 2, right? That's the last point I have. All those points are in the middle. So this point right here, halfway between, is the pi over 4. That's this one. And then these are the 2 points that go right here. Here, pi over 8. and here 3 pi over 8. Then I use the fact that I know the amplitude is 1 because there's just a 1 here, right? And it's not a negative number, so it's not flipped over. So I'm just going to draw my regular old sine function, which starts here, ends here, has a middle here, goes up, back down, back up. So that point's there, that point's here, up, down, up. The important part of this graph is that you've now shown the new period. And that's what's over here on this picture. It's hard to see it, but the blue one, let me get all the other crap out of here. Get the green one, get the red one. If you look at the blue one, y'all see we have the same thing? They're not showing pi over 8. I need to change the scale. Let me see if I can do this. Pi over 16. There we go. All right, do we have the same thing? 0. At pi over 8, it's at the top. Pi over 4, 3 pi over 8, and pi over 2. All right. So what I want you to do, try your best on, we've only done one example. How about I do this? How about I give you the weekend to just get caught up on everything, all right? If you have other homework in other classes, get caught up. You can look at the homework for 7-6 if you'd like, okay? If you want to mess with it, I can tell by looking at some of you, you've seen this before. If you want to go knock it out, you can, but it's not going to be due, all right? The 7-6 won't be due. We need to come back and then I need to give you some formulations for that 7-6. We need to define, you know, what's the period, there's a formula for it, and everything else. We've only done one of these examples. You need more before I send you to the homework.
So is this 7.6?
This is 7.6, yes. The graphs of sine and cosine. All right? But please, before we meet again, please go back and look at your notes. Don't come in here like completely cold on Tuesday, right? Review stuff so I'm not spending time trying to remind you of all this. All right, everyone have a great weekend, all right?
The one that's due today is getting it. Yes, but you know.
Yes. Yes.
Do you want me to hold?
Oh, wait, you know what? I'm recording still, and let me turn this all off.